When we gaze into a clear night sky, we see thousands of bright dots in the sky we call stars. What are these stars made of? How were they formed? Will they remain in the sky forever? These are probably some of the questions early humans thought of as they looked at the beauty of the night sky. Thanks to technological advances over the years, we now have the chance to fully understand and study these stars that were once impossible. Space is filled with gas and dust consisting of mostly hydrogen and helium. When an area has more of these gas and dust particles, over a long period of time, it will start to collapse, heat up, and eventually create a star. This process can be broken down into 7 steps, all detailing how a cloud of dust and gas can form into the powerful stars we know today. The first step of this process is the interstellar cloud. An interstellar cloud is an area in space, typically 10 to hundreds of light years across, having more gas and dust particles than surrounding areas. Because of universal gravitation discovered by Isaac Newton, these particles slowly get drawn in closer together, creating denser areas of gas and particles. This step creates a nebulous with beautiful patterns and shapes, which can even be seen with the naked eye. Nebulas can be classified into different categories: emission nebulae, reflection nebulae, planetary nebulae, supernova remnants, and dark nebulae. Emission nebulae emit their own light. The ionized gas has high energy, allowing them to glow, the most famous one being the Orion Nebula. Reflection nebulae reflect the light from nearby stars. The stars nearby don't have enough energy to ionize the gas, but have enough to scatter the light throughout the nebulae. Planetary nebulae has a cloudy shape that resembles planets. However, these nebulae don't have anything to do with planets. These are created when medium-sized stars die and shed the outwards layer outwards into unique shapes. Supernova remnants form when a large star explodes in a supernova. The debris left behind creates an expanding nebula, the most famous one being the Crab Nebula. Dark nebulae has the highest concentration of dust and gas particles. This causes the nebulas to block and absorb the visible wavelengths behind it, making it look like there's a hole in space. Next in stage 2 is the fragmentation of the nebulas. In this stage, the interstellar cloud breaks into many pieces, creating smaller interstellar clouds still 100 times the size of our solar system. Due to gravity, these fragments shrink as density increases. This traps radiation and causes temperature and pressures to rise. After tens of thousands of years, the third step is the end of fragmentation. The fragments are now around the size of the solar system and has reached a high enough density to where it can no longer break apart. With the temperature reaching 10,000 kelvins, a protostar now appears in the center of the fragment. However, if a nebula doesn't have enough mass to sustain hydrogen fusion in its core, stellar evolution ends here and creates a failed star we call a brown dwarf. Brown dwarfs are best described as an astronomical object between a planet and a star. These brown dwarfs are still extremely large in size, ranging from 13 to 80 times the mass of Jupiter. Due to their inability to undergo stable hydrogen fusion, they cool down over time and emit only light on the infrared spectrum, making them almost invisible to the naked eye. In the fourth stage, contraction begins to slow and the protostar can now be plotted on the HR diagram. In this stage, it is commonly referred to as the T-Tauri phase, named after the first protostar observed in this stage. The protostar with its cloud fragments is now around the size of Mercury's orbit, but is still hundreds of times larger than our Sun and has a luminosity of 1,000 times greater. Nuclear reactions have not started yet, so the large amount of luminosity is entirely due to the gravitational contraction. The material of the gas cloud falls into the protostar, converting potential energy into heat. This part of the evolutionary tract is commonly called the Hayashi tract, which shows the path of a protostar becoming a main sequence star. In this tract, the protostar shrinks and loses luminosity while slightly increasing surface temperature. By stage 5, the protostar has now shrunk to 10 times the size of the Sun and has a surface temperature of around 4,000 kelvins. The temperature in the core, however, is now 5 million kelvins, but despite this, it is still too cool for nuclear fusion to begin. By stage 6, the protostar has now reached a temperature of 10 million degrees Kelvin and is now a true star. This is because nuclear fusion occurs where protons fuse into hydrogen to form helium. This reaction causes a large increase in radiation, increasing the temperature and pressure of the Sun. Stage 7 is the final step where the star stabilizes and becomes a main sequence star. In this stage, the star no longer collapses and reaches hydrostatic equilibrium. This is when the pressure created by the heat of the star equals the pressure inwards by gravity, causing the star to become stable and unchanging in size. From interstellar clouds to a main sequence star, stellar evolution takes around 1,000,000 years and is what every star goes through. The only variance is the mass of the star once this evolution is finished. Once in the main sequence, the star will continue to shine for millions to billions of years. Our Sun is an example of a main sequence star and has been around for around 4.5 billion years, roughly halfway through its life cycle. While a star is alive, there is constant nuclear fusion converting hydrogen into helium. However, all good things don't last forever. In this case, after a few billion years, the amount of hydrogen in a star will eventually run out. When this happens, a star can no longer continue nuclear fusion in its core, thus no longer be in hydrostatic equilibrium. When this occurs, the core contracts, while the mostly hydrogen shell of the star expands outwards. During this expansion, the surface of the star cools and turns into a red color, thus becoming a red giant. In the core, however, temperature rises and starts to deplete hydrogen in the shell faster and faster, causing the star's brightness to increase. The core eventually gets so hot that helium fusion will start, creating carbon as a product. Just like hydrogen, there is only so much helium to burn, and unfortunately for the star, helium is depleted much faster than hydrogen. Beyond this process, the end of stars can vary depending on the mass of the star. For stars similar to the mass of our Sun, once helium is depleted, the core collapses again. When this occurs, the outer layers of the star are expelled in all directions, creating a planetary nebula. What's left behind is a white dwarf, a small ball of carbon that was once the product of helium fusion. These white dwarfs are around 100,000 kelvins and are one of the densest objects in our solar system. While the size of white dwarfs vary, they are usually similar to the size of Earth and are hundreds to thousands of times smaller than the star it used to be. White dwarfs will start to cool down and become darker and darker, eventually reaching the end as a black dwarf. However, there aren't any of these black dwarfs in our universe, as it takes a few trillion years to reach this stage, significantly longer than the age of our universe. Stars classified as a supergiant have a mass 8 to 12 times larger than our suns. These stars end differently than smaller stars and are much more violent. These stars swell up much more and have nuclear fusion with increasingly heavier elements due to the high temperature and pressure in the core. Elements such as carbon, oxygen, neon, magnesium, silicon, and sulfur are fused to eventually accumulate into the creation of an iron core. This is because iron is the most compact and stable element requiring energy the star isn't able to produce. When a star isn't able to release any more energy, the core collapses because of gravity, creating a giant explosion where the outer layer is blasted in all directions. This is called a Type II supernova. What is left behind is a neutron star, the collapsed core of the larger star that exploded. Neutron stars are the most dense objects in the universe. To put it to scale, a sugar cube-sized piece of a neutron star would weigh around 1 billion tons on Earth. Some of these neutron stars have strange characteristics, one example being this neutron star is the fastest spinning object we know in the universe and spins around 43,000 times per second, or around 717 times per second. This makes it twice the speed of an average blender. If the original star had more than 25 times the amount of mass of the Sun and collapses, a black hole is formed. The core of a supernova becomes so compact it collapses on itself, causing gravity to be so strong that even light can't escape. There's another type of supernova called Type I and is much less common. Type I supernovae occur when a white dwarf gets too close to a star and starts taking matter from it. The white dwarf will steal the matter from the star until it reaches a certain mass, causing a supernova explosion.